Alright, I built this circuit a few years back, and I don't know where on the internet I got this circuit, but I don't, I think it's one of those circuits where it was a design out there that, was somebody's idea and they didn't really build the thing, I suspect. Um, so, um, but anyway, I did, build it, right here, this is it. And, this is my version of it. But like I said, right off the bat, I suspect this noise source is actually built wrong because this is how you would normally build a noise source. The whole idea is you got this transistor, okay, and its diode is reverse biased. And, if you know anything about transistors, well, the reverse leakage current on a transistor diode is usually exceptionally good. They're really, really low leakage diodes, apparently, more often than not, anyway. So you look at this thing, you think, well, this will never work. I mean, okay, you're the lowest leakage diode in the world. You're going to stick through and try to amplify in a transistor. Well, the thing is, it's not used that way because you also know a bit about transistor data sheets. You realize that these base emitter diodes are usually only limited about a 5 or 6 volt reverse breakdown. So this is actually acting like a Zener diode, 5 or 6 volt Zener diode. And you're supposed to inject, the whole key is Zener diodes get real noisy when the current is real low. And so if you want to use a Zener diode as a noise source, you're supposed to put really low amounts of current through it. You know, so you're supposed to have, like this guy's got collector feedback going into this reverse diode, which is acting like a Zener. Okay, so that's going to help set his his cue point. 12 to 18 volts being applied. So, you can, do a little bit of simple math and kind of figure out, basically where this thing's going to operate. Because, we got roughly 5 or 6 volt drop here, zero point 0.6 volt drop here. So, you're going to have a 6, 7 volt drop, across this. So, the difference between this and this, is basically going to determine what the bias current is. So, um, and it sort of depends on where your operating point will end up being, but that's going to be set based on your bias current. At any rate, so you could end up with like 6 volts divided by, assuming that's your output. 'Cause your output's going to be certainly, high enough. Again, 5 volts at least. So you can figure, you know, um, they're going to be dealing with pretty low currents here. So, but anyway, that's the whole idea, is to keep this current, a sub milliamp range. And this junction here will generate a lot of noise, and that gets amplified by this transistor, which has maximum gain, because, basically it's RE prime, divided into R1 here is going to give you your gain. So, it's likely going to be pretty darn high. Because, the saturation on this would be, assuming 12 volts would be, somewhere in the neck of the woods of, about 2.5 milliamps, so that gives you a gain, of, about, I mean, it gives you an RE prime of about 10 ohms, so, 470 would be the theoretical gain of the transistor based on that ratio, right? Um, so, anyway, you're going to get maximum gain out of it. So, he's trying to really amplify, you're trying to amplify the noise. Now, I don't know if this capacitor is a really great idea or not, because I built one of these noise source, probably these exact same values actually, and it works great. I don't think I put this capacitor here because it seems like that would eat a lot of your noise, right? I mean, it's a 1 microfarad capacitor, really. It looks like that eat a lot of what you're trying to generate. So, but maybe not. I don't know, but it just seems like it might. Um, yeah, because I mean, like I said, that does make a high pass filter. Maybe he's just trying to eat out the flicker noise or something. The low end stuff, because it'll probably form a RC filter here somehow. So yeah, it might be a good idea if you wanted to limit it. Because I know the one I built had a lot of, the noise curve was like this. So, it was definitely a sharp curve. With the noise drastically increasing as you approach DC. This would probably eliminate some of that. So maybe. So I don't know. But at any rate, the thing as he built it works ish. But again, I don't know if the person that designed the circuit ever actually built it or not. But say I got it, connected to 9 volts because his design was supposed to be 9 volts. Um, and the idea was is to take this noise and stick it through a 386 audio amplifier, right? And and he's got it set to like gain a 200, but then to stick it through a coil and make a signal injector. So you can see the coil there, but it's supposed to be a noise signal injector, and he specified I think 1 loop of wire or something, but I think that's just going to stress out your amplifier if you do that, and you can get the same benefit, with multiple turns. I got like 10 turn coil here. So, but if you turn this thing on, it starts out about 32 milliamps, and you can see the noise coming out, across the coil, which I got my oscilloscope probe right there on the output. But this current does fall as this thing warms up, so eventually it becomes less and less noisy, and it becomes kind of spotty. So, again, given how he designed this thing with no resistor here, I was thinking, well, maybe he's not wanting to overload his amplifier, because it's supposed to be a 9-volt powered circuit. So this might actually reduce the noise level, but then, I don't know, it just seems kind of off base, that you should have a resistor here to limit the base current through this circuit. Here it's these two are going to battle because this is going to put like 5 volts out here, but if it drops below 5 volts, well, its current is going to fall off, so that starts to turn the transistor off, which starts to drop the voltage and everything, which will cause the voltage it starts to drop the current through the transistor, which will increase the voltage across the collector here, which will increase the current. So these things are probably going to be an interplay. Again, it does work, but again, it's probably not optimized. But and if you take the noise source off, because I got it clipped because I cut the circuit, right here. I snipped it so that I could experiment with it. But yeah, if you cut the shit, I forgot what I was saying. But anyway, if you cut the power off, it drops down like 7 milliamps and nothing comes out of it. So, if I undo that clip, it basically, doesn't do as much anymore. But anyway, you can see right here I soldered a lead on, and I soldered that on right up, between the, to the input, basically, of the audio amp, so I could feed a analog discovery signal in it. Because I got intrigued with that. I was like, you could generate, waveforms, right, and stick it into that coil and actually have that be inject an actual signal into your circuit. Now, in practice, I think you'd want something like an inductor on it, like from an RF, like small SMPS inductor or something, and and then have that be a more precise noise injector, but in theory, you could probably do something like that, and so it'd be like a non-contact noise injector. That may be useful. I don't know, but anyway, I thought I would screw around with this circuit, which is noisy, and it's way more efficient noise-wise when I have the analog discovery hooked to it. If I take the analog discovery off of it, which I can do right now, see the noise signal drops down to something like that. So ignore the blue sine wave. That's still that sine wave generator I'm really fond of. Yeah, but the current is still high, but it'll start falling with time. So it'll get, more and more diminished. But that's not really a good generator. But boy, the analog discovery is a good noise generator. And again, I don't have a signal coming out of it right now. But but leaving it like that here in the analog discovery, I got my little probe wired up with an inductor, so I can use it as a pickup coil. So so basically I'll bring this close and far away, and you can kind of see what's going on here. I'm going from pretty much little to no signal to as I bring it closer and closer, I'm right in the middle of the coil now. So we're getting about a 1.5 volt peak to peak out of this little thing. So I mean, holding it right where I have it. So so yeah, I mean it works. But now if I basically turn on the signal generator, I got it set to a 200 hertz waveform. It changes the profile a little bit because I got the thing turned down quite a bit, but I can turn it up. But let's see what we pick up. Okay, it still looks basically the same, but there is a frequency. Okay, so now I turned it up to 50 millivolts injected signal, and you can see what's going on in the scope. Turn it to 100 millivolts, and you can kind of see the current starts to rise. Turned it up again to 200 millivolts. So that's producing that interesting frequency there. Let's see what happens if I change increasing the frequency. So now we're up to 100 milliamps, and it's already, my constant current source is kicked in. So it's exceeded the limit. So but let me reduce it to 100 millivolts. So that's got our power supply happier now. But yeah, so I mean, I do have basically a controlled noise source here, that generates group noise pulses. And it wasn't actually doing this the first time I hooked it in, but I was running it at different voltages and so forth. But like I said, you can see right now I've got it up to 175 hertz. At 100 millivolt sine wave is what I'm injecting into it. But now let me do the coil thing now, and so you can already see, even though I'm pretty far away from the coil, I'm already starting to pick up. And I've got my thing, my scope set to 500 millivolts per division. So, but even at this distance, I'm picking up on it quite a bit. So, but as I draw it closer and closer, you can see, that yeah, I mean, we're picking up some interesting waveforms here. So, and this is coming from the actual coil versus scope is just hooked to the output of the coil. So you're seeing, something that looks more garbagey, but you can kind of discern a little waveform in there. With me holding it like that. So, but let's see what happens. As I increase frequency, it does that. I'm trying to hold the coil in place. We're up to 200 hertz or so. I'm decreasing the frequency. 36 millivolts. I can probably turn it up and double it. Okay. But yeah, this thing, seems to change, as it heats up. It's 74 milliamps or so. Yeah, I just exceeded the limit when I went to 100. Let me reduce that. Okay, we're at 85 milliamps from the power supply. And I can't hold it steady and hold the camera at the same time. But But yeah, I mean, it's 2.2 kilohertz. So like I said, it occurred to me that, like I said, yeah, you do this, you put it on a different amplifier. You build a more powerful amplifier with the transistors or what have you, and or you could buy like a car stereo audio amplifier chip. Those can be pretty powerful and they're cheap. Like a couple of bucks. And hook that up to this thing, and that could generate some serious power. And again, put maybe a proper inductor, or at least use a lot more turns of coil. But you can inject a signal. In fact, you can make one that is like mine, that has a noise source on it, but you can also put a pure waveform into it, because basically I'm applying a pure waveform directly to the input of this 50 kilo ohm LM386. And you know so we're only getting, so because it's supposed to be AC coupled, I'm just directly injecting it, right? So that's why we're getting kind of a not really full waveform. But this way I am able to inject the noise on. I'm probably fucking up the 386 doing that, come to think of it, because you really shouldn't inject a signal that way unless it has a DC offset built in. But at any rate, just for testing purposes, it's very interesting. But like I said, if you had a more powerful amplifier, you could just keep it an air inductor and just wind more turns or whatever, but make it tighter winding or something, so you can inject signals, into a definite area of your circuit. But again, having an inductor similar to this one, tied to it. And I don't know if this is an RF choke or not, or a regular inductor. I got it out of some piece of equipment. I guess I could try to look that part number up, but it's about 1.2 millihenry, I think I measured it at. But the difference between an RF choke, is RF choke, has kind of a square BH curve, whereas an inductor will have more of an S curve. The square curve inductor is always a sign of high loss, and that's what two-terminal RF chokes do, is they actually absorb they're trying to absorb energy. So I don't think the common mode chokes are like that, because they're actually designed to have one waveform cancel the other. I don't, that's, I think, the whole principle of the common mode choke. So I don't know that they're lossy as much as a choke is. But this could very well be an inductor. I don't know what I got it out of, but I definitely desoldered it out of something. So, yeah, I keep fucking my circuit up here. Anyway, but yeah, that about does it. So, for this, just an interesting little deal. Cheers. Oh, and by the way, this is the kind of waveforms you get without the analog discovery hooked to it. I went ahead and tried hooking my decade box to it too, to try to see if I could, put some, resistor into that base, and wow, that's really, that's generating a lot of noise, really kind of freaking out my power supply, apparently. That's why I'm getting this result. The power supply is not handling this frequency very well. I mean, I've noticed that, I got like like walkie-talkies and stuff like that, really fucks with these power supplies quite a bit. It helps when I, turn that resistance off. I've got no resistance applied to it right now, at least none to speak of. So, yeah, well, actually, it's freaking out because it's right at the cusp of being too much noise. Here, let me, yeah, that thing's trying to draw a lot of current, so, yeah, it's like it can't decide what it wants to do, so there's no way you could power this off a 9-volt battery. So, it's very interesting. So that's why I get, because even nothing hooked to it, that's what you get. Okay, it's 15 milliamps and or 11 milliamps and falling, and it's becoming sporadic, and that's what we're picking up off the probe here. So that's certainly not a very good noise source. So, but like I said, with them shorted, like I had it originally, you know, yeah, it's still kind of generating these little peaks and valleys here, you know, as the CCS tries to figure out what it wants to do. So, yeah, I mean, that's not good because this thing, you don't want to put even 1 amp of current into this fucking thing. And, you know, because it's only like a 700 milliwatt amplifier. So, I mean, you don't even want to put more than 100 milliamps into it. So that's why I'm trying to limit it. But, yeah, so this thing's got dodgy behavior. And, you know, and even if I, again, try to put you know, put like 30K of resistance in it, you know, it just freaks out even worse. So, I mean, it's like I said, you know, I kind of doubt this person ever actually built this circuit, really. It was certainly better behaved with analog discovery hooked to it. You know, even though, again, you know, I'm kind of clipping the amplifier because you shouldn't do this. But saying it's a lot more stable now, the current's a lot lower, you know, and, you know, we do produce a good noise pattern with the pickup coil. So yeah, I mean, I don't know, dodgy internet circuitry, I suspect. But at any rate, so that ought to handle this video. So cheers.